Good evening, everyone. Today we will talk about three-phase power relationships. If we have time, we're going to talk about three-phase power correction. Right. So the real and reactive power for three-phase circuits. There are two ways to look at it. So let's say we have phase A, phase B, phase C, right? And then we either connect a Y load like this, or we connect a delta load like this. Right? Either way we connect the loads, we can talk about the power dissipated per phase. The phase could be this Y phase, it could be this delta phase, right? But whatever it is, the power dissipated per phase is going to be the phase voltage, right? And then the phase current, the current going through that phase, times cosine theta, where theta is the angle between the voltage and the current. That's what real power is, right? That's of course VP and IP has to be represented in RMS, right? For this to be valid, or else there's gonna be like if this was peak, there will be like a factor of 2, a factor of half. So remember that, okay? And then QP is VP IP sine theta. Okay, now this is in terms of the phase voltage and the phase current and the load, whether it's Y or delta. Let's say we want to write it in terms of the line voltage, or what we call line-to-line voltage. Line-to-line or line voltage is the same thing, and the line current. Of course, the line current is this, right? This is IL, and this is VL. So this is VL, and this is IL. I'm just writing the magnitudes here. I'm not writing the phase, the full phasors, right? So for a Y load, right, it's clear that the phase current, the current going through the phase, is equal the line current, right? And then the phase voltage, though, this voltage here, VP, is not the line voltage, is the line voltage divided by square root of 3. So this is the relationship that we established. And then for the delta load, the phase current, which is equal to the I delta in this case, because each phase is those are the phases of a delta connection, right? So the phase current going here, this is IP or I delta. We derived that in the last lecture. That equals IL divided by square root of 3. And then VP in this case, the voltage across the phase here is equal to VL, equals the line voltage. Right. So it turns out that the power per phase, if I want to write it in terms of the line voltage and the line current, it turns out that it doesn't matter whether the load is delta connected or Y connected. When I multiply VP by IP, I'll get the same thing, right? Because here I multiply VP by IP, I get VL IL over square root of 3 cosine theta. But if the load is delta connected, I get the same thing, because now the square root of 3 goes to the other variable in the power equation, goes into the current variable. So the same thing, I get VP times IP is VL times IL over square root of 3, right? So for the Y connected load, VL over square root of 3 is the voltage times IL, and then for the delta connected load, IL over square root of 3 is the current times the VL. Either way, we get the same final expression. Okay, and then QP is going to be VL IL square root over square root of 3 sine theta. So this is the expression of the power per phase using the line variables for the voltage and the current. There's an extra square root of 3 factor there, in contrast to those equations, which are the straight phase voltages and currents. Right? So this shows up. Square root of 3 always shows up when we're talking about three-phase circuits, balanced three-phase circuits. Of course, the total power is going to be, this is power per phase, consumed per phase. The total power is going to be just the sum of all three phases. So it's going to be 3 times this. 3 times something over square root of 3 is just going to be square root of 3 VLIL cosine theta, and then Q of t is going to be square root of 3 VLIL sine theta. Okay. So what is the magnitude of the complex power? Well, we know that it's just going to be PT squared plus QT squared, right? That's the magnitude of the complex power. So take this and let's do this. So this is going to be PT squared is just going to be 3 VL squared IL squared cosine theta squared plus 3 VL squared IL squared sine squared theta. So taking 3 VL squared IL squared out, we end up with cosine squared plus sine squared, which is 1. Right? So we end up with square root of 3 VL IL. Right? And then, of course, the angle of S of t is just going to be theta. That's what it's going to be. Right? The power factor angle is the angle of the complex power. We've established that. All right. So nothing new here. The only new thing here is that to mine the square root of 3 term, when you're calculating the power per phase using the line voltages and currents, and to note when you're calculating the magnitude of the complex power, total magnitude of the complex power, note this extra square root of 3 when you're using VL and IL. That's the only difference. Everything else is the same. Okay, so let's do an example. So we have a Y delta system with a line voltage with VL being 208 VRMS. The total power consumed by this system we know to be 1200 watts. And there's a power factor angle of 20 degrees lagging. Okay, so what we need to determine is two things. The magnitude of the line current, IL, and Z, the value of the impedance per phase. This is a delta connection, right? So the Y is the source, delta is the load. So this is going to be Z delta. So you want to find the Z delta per phase, per delta phase. So this is Z delta, and Z delta. Okay, so yeah, let's solve this. The solution, right? So the total power is 1200, right? But what's the power per phase? Power per phase is just 1200 divided by 3, right? We have 3 phases, so it's going to be 400 watts. We know from our equation that power per phase is VLIL over square root of 3 cosine theta. We know theta is 20 degrees, right? We want to calculate IL. We can use this equation to calculate IL, right? So 400 VL we know is 208 over square root of 3 IL cosine 20 degrees. So that tells me that IL is going to be square root of 3 400 over 208 cosine 20 degrees. Put it in a calculator and you get 3.545 amps RMS. Okay, so this is the first part. The second part, well, we want to calculate the impedance. To calculate the impedance, here we know VL. It will be helpful if we know I delta, right? Which is IP here in this case, for the load. Right, so it will be helpful if we can know I delta so that we can divide VL by I delta to get Z delta, right? So IP, which is the same as I delta, we established last time that that equals IL over square root of 3, right? So we know what IL is. We calculated it here. So it's going to be 3.545 over square root of 3. That's going to equal 2.05 amps RMS, right? So we have the line voltage and the line current that allows us to at least calculate the magnitude of Z delta. So that's going to be VL over I delta, which is 208 over 2.05, which is 101.46 ohms. We're not done yet. We need to find the angle, right? What's the angle? Well, the angle is the same as the power factor angle, right? What's the power factor angle? The power factor angle is the angle between the phasor current voltage and the phasor current, right? So that's the power factor angle, and we say it's lagging, right? Meaning that the current is behind the voltage, meaning that the angle of the voltage minus the angle of the current gives me a positive delta, right? So that tells me we take a positive value of 20. If it was leading, we put minus 20 degrees here. But because it's lagging, we put 20 degrees here, right? Because Z delta equals VL over IL. It's lagging, so IL is behind VL. So the angle of so it's going to be theta V minus theta I. Theta V is larger than theta I because it's lagging, because I is lagging V. So the angle should be positive. So we have 20 degrees here. So this is Z delta. And writing it in rectangular coordinates, we get 95.34 plus J 34.7 ohms. And this is Z delta in rectangular coordinates. Okay, let's do another example. Okay, so we have a Y to Y connection. Right, and then we have the phase voltage being 120 volt RMS, and then this Y to Y connection. Let me draw it this way. Before it goes into the load, there's some line impedance. This is actually a previous example that we solved last time. It's example 11.2 in the book, but we want to calculate the power for this example now. Right, and then after the line impedance, there is a load impedance like this. Right, and then we solved this already. So what we want to do is we want to use the values that we solved already to get the load power, the load apparent power. Let me say it this way: the load complex power, which is going to give me P and Q, P load and Q load, and then the load, the source complex power, which is going to give me P source and Q source. So I want to find out how much P and Q I'm sourcing and how much P and Q are going to be appear at the load. They won't be equal because there's the transmission line here, there's the line impedance here that is going to consume some power. Okay, so we said we solved this circuit already. Z line is the same as that example. It's going to be 1 plus J omega, and Z Y, the load, is going to be 20 plus J 10. So we solved this already. We know that we can solve it by solving a single phase. So that's going to be 120 0 degrees. That's VAN. Then IA. and then the line impedance 1 J1 ohms, and then the Y load, one phase of the Y load 20 J10, right? So when we solved this, we found that VAN, the voltage at the load, is going to be 113.15 with an angle of minus 1.08 degrees volt RMS. And then we found the current in the line to be 5.06 minus 27.65 degrees amp RMS. So we want to use those currents and voltages that we solved to find S load. S load in this case is going to be just V load times I load conjugate, right? V load is going to be VAN essentially, which is 113.15 minus 1.08, and the current is going to just be the line current conjugate, meaning the angle now turns positive. So we have 5.06 27.65 degrees instead of minus 27.65. So if I multiply those two together, I end up with 512.1 plus J 256.1. So this is the power at the load for a single phase, right? So this is in watts, and this is the reactive power at the load. It's P. Let me put in P to indicate a single phase, which is, so this is in watts, 512 watts, and this is going to be 256.1 VARs, right? What about the apparent power? So this is S load magnitude. It's going to be the magnitude of this thing, which is going to be 572.539 VA. Okay, so yeah. What about the right? You know how to find that, right? You take 512 squared plus 256 squared, right? You take the square root of that, and that should give you the apparent power. So this is in VA. Okay, now what about the source? So what about the S source? That's going to be V source, of course, phasor times I source phasor complex conjugate, and we know what the V source is going to be. It's going to be 120, right? So this is going to be 120 0 degrees, and then the current is the same, which is 5.06. Because it's conjugate, we have positive angle 27.65 degrees. And when we calculate this, we get 537.86. This is the P source per phase in watts, plus J 281.78. This is the Q per phase for the source. So this is in VARs. Okay, and then of course the magnitude is the magnitude of the apparent power is the magnitude of S source, right? So the apparent power is the magnitude of S source, right? And so if we calculate that, that will give us the apparent power. What is, by the way, the total power sourced? Well, it's this the number that we got here is the power per phase, right? So the total power source is going to be just this times 3, right? So if I take this multiplied by 3, I end up with the total power being let's call it PT, PST. That's going to be 1613.57 watts. And then QST is going to be 845.348 VARs, right? And then S source total is going to be the magnitude of this times 3, which if you do the math turns out to be 1821.6 VA. All right, and this concludes this example. Let's do the next example. Okay. So the next example statement is as follows. So we have a three-phase source connected to three different three-phase loads, right? And this connection is in parallel. So I have my three-phase source A, B, C connected to load 1, and then I have, this is a three-phase load, and then I have load 2, L2, and then I have load 3, L3, and they're all connected in parallel in this manner, right? And then this goes here. So it's a parallel connection of loads. Load 1 is described as following. It's a 24 kilowatt load with a 0.6 power factor lagging. Load 2 is a 10 kilowatts load at unity, meaning we have unity power factor. The power factor is 1. And then load 3 is 12 kVA load. Notice it's given in a different manner. Here we're given the real power. Here we are giving the apparent power, but it's at 0.8 leading power factor, right? And then the line to line voltage, or the line voltage, is 208 VRMS at 60 Hertz. So what we're trying to find is what is the line current and what is the combined power factor of the three loads. If we consider all these three parallel connected loads to be one equivalent load, what would be the combined power factor? So let's call that PF combined. Okay, so let's do the solution. So, I mean, given this information, we can calculate S1, right? S1 is just P1 plus J Q1. We know what P1 is, right? P1 is just 24,000. But what's Q1 in this case? Well, we know that Q1 over P1 is tan theta 1, right? It's the angle of the complex power is the power factor angle, right? But tan theta 1 is sine theta 1 over cosine theta 1. Cosine theta 1 is the power factor, of course. It doesn't matter if it's leading or lagging. The power factor is always going to be positive because cosine is always going to be positive, right? So it's going to be sine theta 1 over the power factor. So that tells me that gives me the equation to calculate Q1. Q1 is going to be simply P1, take P1 to the other side, over the power factor times sine theta 1. Right? So Q1 is going to be 24,000 over 0.6 times sine, what's theta 1? Theta 1 is a power factor angle. So it's going to be cosine inverse 0.6, right? And because it's lagging, sorry, that means that the current is always going to be behind the voltage, right? So that means that the angle itself is going to be positive, because you know the angle is going to be the angle of S is going to be the angle of the voltage minus the angle of the current. Because the current is lagging, that means this angle, which is the angle of the voltage minus the angle of the current, which is the angle of S, is going to be positive. So when we take the cosine inverse, we discard the negative possibility and we only take the positive possibility. So this angle turns out to be 53.13 degrees. If we do this calculation, we end up with Q1 being 24,000 over 0.6 times sine 53.13 degrees. So Q1 equals 32,000. So now we can write S1 completely. S1 is 24,000, which is the real power, plus J 32,000, which is the reactive power. Okay, and then S2 is given as 10 kilowatts, 10,000, but it's a unity power factor, meaning there is no. What does unity power factor mean? That means that cosine theta is 1, meaning theta is 90 degrees. Sorry, theta is 0 degrees. Theta 1 is 0 degrees. What's sine 0, right? Sine 0 is 0, so there is no reactive power. So we have plus J 0, and then S3 is given as apparent power, which simplifies things. It's given as 12,000 kVA with an angle of minus 36.9 degrees. Why? Because this is why negative? Negative because the power factor is lagging, and the minus 36.9 degrees comes from the cosine inverse of the power factor, which is 0.8. It's cosine inverse 0.8. Okay? And now it's leading, meaning that the current leads the voltage, meaning that when we calculate S, we take the angle of the voltage minus the angle of the current, right? But the angle leads the current leads the voltage, so this angle is going to be negative, going to have a negative sign. Okay, that's why we put minus 36.9 minus cosine inverse 0.8. Right? If I convert this to rectangular coordinates, I get 9600 minus J 7200. Okay. Now we know that the total complex power is conserved, right? So S load is going to just be equal to S1 plus S2 plus S3. So if we combine all those three complex powers, we find that S load turns out to be, well, 10,000 plus 12,000, 24,000 plus 10,000 is 34,000. 34,000 plus 10,000, let's say, is 44,000 minus 400 is 43,600 plus J 32,000 minus 7,200 is just 24,800. Converting this to polar form, we end up with 50, 159.7, 29.63 degrees. And yeah, so we want to calculate the line current, right? So we know we know from this equation that S load, we derived this equation previously, right? S load is square root of 3 VL IL. That's the relationship between the magnitude of the complex power and VL and IL. There's an extra factor of square root of 3 here, right? And we calculated that at the beginning of the lecture. So that tells me that IL is going to be S load magnitude over square root of 3 VL, which is 50,159.7 over square root of 3, 208. So this gives me IL equals 139.23 amps RMS. This is my first thing I wanted to calculate. And then what about the power factor combined? It's just the angle of S, right? It's 29.63, so it's going to be cosine 29.63, right? So it's going to be 0.869. And is it leading or lagging, by the way? Well, the angle is positive, right? S load is positive, the total S load, which means that the voltage is leading the current is lagging the voltage. So this is going to be 0.869 lagging. All right, and this concludes this example. So we want now to redo this same example, but we want to assume that there is a line impedance. So assume, this is the second example. So assume a line impedance as follows. Right, so what's happening here is that we have our load, three-phase load, and we calculated in the previous example we know what the line voltage is at that load, and we know what the power factor is, and we calculated the line current. Right, this is what we did. Right. Right, and this is, by the way, the equivalent load. So here I'm presenting all the equivalent of all three loads. So all the three loads are connected in parallel, and this is the equivalence or equivalent of them. Right, and then now the assumption is that there's some kind of line impedance in between. This is a impedance representing a transmission line, and then I have my source here. Right. The question is, what is the power factor at the source, and what is the line voltage at the source? Okay, so that's what we want to solve for. I mean, this is simple. We already know S load, right? So, and we know IL. Knowing IL, that will allow us to calculate S line. And then from the conservation of complex power, we know that the S source is going to equal S line plus S load. Okay, so that's how we are going to proceed. What's S line? Well, let's do a little bit of review. So recall that if I have some kind of impedance R Jx, then I have my current phasor going in, and then my voltage phasor. Recall that S equals V. Right, so I have Z. This is the impedance. And I want to write S in terms of Z. We did that, but I'm going to review it for you. So it's going to be S V phasor times I phasor conjugate. What I can do is I can multiply this here by I over I, right? So I end up with V over I times I conjugate. I didn't change a thing, right? I just multiplied by I over I. Right, now what's V over I? V over I is Z. What's I times I conjugate? What's a complex number times its conjugate? It's always its magnitude squared. So this equals magnitude I squared. Okay, so S going through S line for an impedance is just the impedance times the current going through the impedance squared. So what is S line then? S line is going to be, well, in this case, we have three lines, right? So it's a three-phase system. So we're going to have the factor of 3. Then I'm going to put in Z. Z is 0.05 plus J 0.02. And then the current flowing squared is going to be IL squared, right? So what is IL squared? We found it in the previous example to be 139.23 squared. If you do this calculation, you end up with S9 being 2907.75 plus J 1163.1 volt amperes. right? So S at the source is just going to simply be S line plus S load. And we found S load in the previous example, and we know what S line is now. So S load is what? It's from the previous example, it was 53,600 plus J 24,800 plus 2907.75 plus J 1163.1 VA. Sum everything up and change it to polar coordinates. We get 53,264 with an angle of 29.173 degrees VA. Okay. All right. So what's VLS in this case? What's the line voltage at the source? Line or line to line voltage, the same thing. It's going to be just SS over square root of 3 IL. We established this formula in the beginning of the lecture. So we know SS, it's going to be the magnitude, right? Let me write it this way, magnitude, right? So this is the magnitude, I plug it in, and then I know square root of 3, I know IL, which is 139.23. Plug everything in and calculate that, it will be 220.872 VRMS. That would be the voltage at the source. That would be the line voltage here. Okay. What about the power factor at the source? Well, I mean, the power factor is the cosine of the S angle, of the cosine of the angle of S. Right, so it's going to be cosine, what? Oh, 29.17 degrees. The angle is positive, so it's going to be lagging. So the power factor at the source is going to be 0.873 lagging. All right. Do the final example before we move on to power factor correction in three-phase circuits. Yeah, so the example is as follows. We have two three-phase systems, system X and system Y, and assume there's an impedance between them. There's a three-wire impedance between them. So we have 1 ohm, J2, 1 ohm, J2, and then 1 ohm, J2. So those are nodes A, B, C. Those are nodes capital A, capital B, capital C, and then there's a neutral wire between them. So this is small n and capital N. Right, and then we know the voltages across the two systems. So we know the VAB is 12.0 degrees kilovolt, and VAB capital is 12.5 degree kilovolts. So the voltages are equal, but there's an angle difference between the two line voltages. So from a power perspective, the question is, which is the source and which is the load? Meaning, how is power, another way of asking the question is, how is power flowing through this interconnection? What is sourcing power and what is absorbing power? Is system X sourcing power, or is it system Y? Is system X absorbing power, or is it system Y? And the other question is, what is the average power that's flowing, that is supplied and absorbed? Okay, so this is an interesting problem, and it leads us to one basic result that you will get to when you study power systems or introduction to power systems, and I'll discuss that at the end of the example. All right, so first, to solve this, we have to solve for the line current IAA, right? If we know the line current, we can multiply the line current by the voltage to get the power, right? So, and we want to use the trick of reducing, this is a balanced system, so we're going to reduce it to a single phase circuit. The single phase circuit is going to look like this. So this is node A, node N, then I have 1 ohm, and then I have J2, and then I have capital A, and then I have capital N. And the phase voltage is going to be the same as the line voltage, but divided by square root of 3. Right? Not just divided by square root of 3, it's behind by minus 30 degrees, remember? So we derived that in the previous lecture. So if this is 0, the phase voltage is going to be behind by 30 degrees. This is VAN, small n, and then V capital A, capital N is going to be 12 over square root of 3. This is 5 behind by 30 degrees, is going to be minus 25 degrees kilovolt RMS. Kilovolt RMS. Okay. So now we can calculate the current. So this is IAA. IAA is just going to be VAN minus V capital A in capital over Z line. So that's going to be 12,000 over square root of 3 minus 30 degrees minus 12,000 over square root of 3 minus 25 degrees. The whole thing is over 1 plus J2. We calculate this number, I mean nothing fancy here. IAA turns out to be 270.299, 179.1 degrees ARMS. Okay. Now we are in a position to calculate the power. What is PY? The power, average power dissipated in system Y. So let's go back. Now we want to go back to the three-phase perspective. We used the single-phase equivalent circuit to find IA, and now we use our equation for the power absorbed by Y. We know what that equation is. It's square root of 3 V line, which is VAB, I line, which is IAA, and then cosine theta V minus theta I, right? Here in this case, this is the phase voltage and the phase current. Remember, that was what the cosine theta in the power equation was representing. It was representing we started with the VP, IP, cosine theta. So theta represents the angle between the phase voltage and the phase current, right? So it's the angle between this voltage and this current, right? Which is what? Which is minus 25 degrees minus 179. So this is equal to square root of 3. What's VAB? Magnitude is 12,000. 270.299. Cosine minus 25 degrees. VAN capital minus 179.1. If we calculate this, we end up with a negative value. We end up with minus 5.128 megawatts. So system Y is not a source. Is not a load, sorry, not the load. Here we calculated the absorbed power, and the absorbed power turned out to be negative. That means system Y is the source of the power. Okay. What is the power then absorbed in the load, which is X? Well, it's going to be square root of 3 VAB small IA capital A. Right now we want to find the current flowing into system X, which is the opposite of I small a capital A, right? Right. This thing here is going to be minus I from A to capital A. Right. Cosine the phase voltage minus the phase current, the phase of the current. So the phase of the voltage is minus 30. So this is going to be minus 30 degrees minus 179.1 degrees right? And this is square root of 3, 12,000. This is the negative, so this is going to be minus 230, 270.299. Cosine minus 30 degrees minus 179.1 degrees. If we do this calculation, we end up with 4.909 megawatts. Aha, so the absorbed power in system X is positive. So that means system X is the load, while system Y is the source. Notice there's a difference in the power. So power that's source is 5 point some megawatts, 5.1 megawatts, while the power that's absorbed is 4.9 megawatts. Where is the difference going? The difference, of course, is going into the transmission line impedance, or the impedance between the two systems. Okay. The interesting thing here is that this is showing us that the power flowing from system Y to system X, in a way we can say it's dependent on the difference of the angle, because the VAB and V small and VAB capital have a difference in angle. This is the reason power is flowing between the two systems, right? If there was no difference in the angle anyway, VAN minus VAN capital is going to be 0, so IA is going to be 0. There'll be no current flowing, there'll be no power flowing. It's because there's a difference in the angle do we get a current flowing between the two systems, and that leads to active power flow or average power flow. This is a basic result that you will discover when you study power systems. It turns out that between two systems, if we have an inductance between them, X, right, Jx, or J omega L, it turns out that if I have a voltage here on a certain angle, V1 theta 1, and a voltage here 2 theta 2 and a certain angle, it turns out that the power flow is going to be proportional to theta 2 minus theta 1. The power flow between those two systems is always going to be proportional to the difference in the angle. It's not going to be dependent on the difference of the magnitude. It turns out that the Q flow, so this is P, the reactive power flow between the two systems is going to be proportional to the difference between the two magnitudes of the voltage. So this is a basic result in power system analysis that when you take that course, you will study it in the first couple of lectures. But that's like an interesting result. Right? It is the difference in the angle between the different locations in the power system that determines the power flow. And we showed that using basic circuit analysis in this example. All right, and this concludes this example. So perhaps let's do now a power factor correction example. And with that, we will end this chapter about polyphase circuits. We're going to do testing 1, 2, 3. Testing part 1, 2, 3. So we're going to do a power factor correction example in 3-phase. And then we will be done with the chapter on polyphase circuits, and we will move on. So okay, so let me state the example. First, I mean, to do power factor correction in 3-phase circuits, it's the same deal. You have to add capacitors in parallel to achieve the power factor correction. The only thing is here in this case, it's not a single capacitor you're going to add. It's going to be a 3-phase capacitor. So it's going to be either a delta connected 3-phase capacitor. So you'll have 3 capacitors actually, or a Y connected set of capacitors like this. But it will be capacitors that are going to do the trick. All right, so the example is as follows. We have a three-phase source. Of course, it's all balanced. Solving unbalanced systems is way more complicated, and we're not covering that right now. We're only limiting ourselves with balanced circuits. Right, so we have a three-phase source that connects to a three-phase load, and the source has a line voltage, meaning this voltage, this is VL, of 34.5 kilovolts at 60 hertz, and the load is 24 megavolt amperes MVA with a 0.78 power factor lagging. So as you can see, it's not a very good power factor. So our goal is to add some kind of capacitors so that we can increase the power factor to 0.94 leading. Okay, and as I said, we could either connect capacitors as Y or delta. Let's do the Y. So if we do the Y, this is the neutral connection, right? So the Y would look like this. I have capacitor 1 connects to phase A, capacitor 2 connects to phase B. This is A, B, C, and then capacitor 3 connects to phase C. So this is a Y configuration, A, B, C. Right? So the question is, what value of capacitance do we need to add in to achieve this improvement of power factor, to go from 0.78 power factor lagging to 0.94 power factor leading? Well, the same technique as that we applied in the previous chapter when we covered power factor correction, but now it applies to three-phase circuits. So we start with S old. What is S old? The S at the load before we add the capacitors. So that's 24 MVA, right? So I'm giving you the apparent power here, MVA. So it's 24 MVA with an angle. What's the angle? The angle is the power factor angle. So it's the cosine inverse of 0.78. And it's positive because the power factor is lagging, right? Because S is V over V times I conjugate. So it's the angle of S is going to be theta V minus theta I, right? So, but because I is always lagging, theta V minus theta I is always going to be positive. So this angle is going to be positive, right? So if I do the math here, if I put this inside the calculator, I'll get this value for S old. I'll get 18.7 plus J 15.02 MVA. Okay. Right. So this is, by the way, theta old. Right. This is the theta that corresponds to 0.78 power factor lagging. What about theta nu? The theta that corresponds. What would theta be if I improve the power factor to 0.94 leading? Well, theta nu would be cosine 0.94, cosine inverse 0.94, but because it's leading power factor, meaning in this case the current is leading the voltage, so the angle of S is going to be the angle of V minus the angle of I. The angle of S is going to be negative, and that's because the power factor is leading, right? So if I calculate this, this turns out to be minus 19.95 degrees. Okay. So we want to add caps so that S nu has this angle. What is S nu really? S nu is just P old plus J Q nu. This is a basic fact about doing power factor correction. We're adding caps in parallel, meaning those caps will not consume any real power. Those caps will only change the reactive power, right? So P old is going to remain the same, right? Q will differ, and we'll get from Q old to Q new, and that will increase the power factor. Now we know that Q new over P old is the tangent of theta nu, which we know what it is, right? So we know we have a relationship here that can tell us what Q new needs to be. Q new needs to be P old times tan theta nu. We know theta nu, we know P old, so we know what Q new needs to be. So S new now in this case is going to be P old. Remember, the average power does not change. Adding a cap just changes the reactive power. And then Q new, we found it here to be P old times tan theta nu. So it's going to be plus J Q P old, which is 18.72, times tan theta nu. Theta nu, we calculated it to be minus 19.95 degrees. This is MVA. And I can calculate this. I end up with 18.72 plus J 18.72 with an angle, the tangent of minus 19.95 is going to be minus 0.362982 MVA. Calculate this, it's going to be 18.72 minus J 6.8 MVA. Okay? All right, so this is S nu. We said complex power is conserved, right? So the S nu should be larger than S old. The difference between S nu and S old should be the complex power that goes into the cap, right? So it's established. We know that the difference between S nu and S old is S cap. The S that needs to be consumed by the caps is just S nu minus S old. If I do S nu minus S old, as I expect, the real part cancels because it's only capacitors. We don't have any resistors there, and I end up with minus J 21.82 MVA. So I end up with minus with Q that is negative, which is consistent with a cap. Positive Q is consistent with an inductor. Okay, so this is the amount of reactive power that the caps need to generate. But remember, there's a difference here compared to the single phase case. Here we have 3 caps. So this amount is going to be divided over 3 caps. So we need to take this amount and divide it by 3 to find the amount per single capacitor. So that equals, well, what's the reactive power coming from a capacitor? We know it's equal to minus J omega C V RMS squared, V cap RMS squared. If you don't remember how we got this, remember that S of the cap equals VC IC conjugate, and can I use Ohm's law to write, instead of IC, and I can write VC times the admittance of the cap, which is J omega C conjugate. When I conjugate this, I end up with VC conjugate minus J omega C, because the conjugate of J minus J. Any phasor, any complex number times its conjugate gives me the magnitude squared. So this becomes magnitude squared, and then minus J omega C. This is how this term shows up. Clearly now minus J cancels with minus J. Omega is just 377, that's 2 pi 60. 2 pi 60 is approximately 377. VRMS squared, what's the VRMS? VRMS is notice our cap set up here is Y connected, so we need to find the phase voltage across the single cap. The phase voltage is just the line voltage, kilovolt, divided by square root of 3. This gives me the line voltage squared times C equals 21.82 over 3 MVA. Okay, so yeah, so we can square this, so this becomes 377. Square root of 3 squared is 3, and then this becomes 34.5 squared. kVA squared becomes MVA, sorry, MV, megavolt. kV squared becomes MV. C equals 21.82 over 3 MVA. M cancels with M, the mega cancels with the mega. And then we can rearrange terms and only C is unknown. So this gives us the capacitor, the value of the capacitor to be 48.62 microfarad. This is the amount of capacitance required to improve the power factor from 0.78 lagging to 0.94 leading. All right. So with this example, we conclude our discussion of polyphase circuits, balanced polyphase circuits. For unbalanced polyphase circuits, things get more complicated. You will have to go back and do mesh and nodal analysis on the different phases. All the assumptions that we had for balanced circuits don't follow anymore, right? That's why balanced circuits are a very important special case, and we try always to maintain balance when we implement three-phase systems. All right, so thank you guys. We're done with this chapter, and then we're gonna move on to the frequency, the last two topics of this course, which are the frequency response, and then after that, of course, the Laplace analysis, Laplace transform. All right, guys, thank you. See you next time.